Hello, my name's Vallieres and I'll be talking about KVL and AC. So KVL is a circle analysis technique used to define unknown voltages. You use the conservation of energy, it's based on it. The basic idea is that the sum of voltage in a closed loop is zero. It can be used in both AC and DC circuits. So as you can see, the voltage source is equal to the voltage drops in the components within the circuit. So you can get this equation: voltage source is equal to the sum of the voltage drops within the circuit. This is two equations describing voltage in different ways. This is the polar form of voltage with the phase angle afterwards. So if the angle was 20 degrees and the voltage was 20, you would describe it. Is that kangaroo? I hate kangaroos. The voltage would be described as 20 within degrees, 20 degrees, 20 volts, 20 degrees. Okay, here's an example. If you had the source of 30 degrees root 2 sine 100 plus 20 degrees, and you had these two, 8 sine 100 t plus 5 and 4 sine 100t plus 70 degrees, and then you had VR, you could solve by using a couple formulas and a couple methods. First, you have to convert them into polar form. So we know this equation: the voltage source will be equal to V1 plus V2 plus VR, but we have to convert them into polar form first. So you've got E equals 30 root 2 sine 100t plus 20 degrees. You can convert that into 30 angle 20 degrees. You can do this. You can use the same method to convert these two voltage equations into polar form, just by dividing the amplitude by root 2 and then having the angle at the end. Okay, so now that we've got them into polar form, we can express it by replacing V1, V2 and VR, or V1, V2 and the voltage source, with their real numbers, their real values. Once we've done that, we can convert them into rectangular form and add like terms to get 21.63 plus 7.1 J. We can then convert them back into polar form, 22.8 with 18.2 degrees, and then we can express them back into this equation, and that's how you solve it. Now, what is it, butterflies? Good, no more kangaroos. Is that a kangaroo? God damn it, I hate kangaroos.